Next, I talk about the SciPy.Spatial Module. As you can already imagine, spatial talks about space, distance, and things like that. So let's see what we have to do with the SciPy Spatial Module under scientific computing under the SciPy library. So we have a comprehensive and systematic guide in that way. The SciPy.Spatial Module provides tools for distance computations, spatial data structures, nearest neighbor search, computational geometry, convex hulls, Voronoi diagrams, Delaunay triangulations, KDTree acceleration. Of course, you can already see this has a lot to do with, space and space and moving around, right? Like I can already imagine that some of these concepts are well deployed in our GPS systems. So when you use Google Maps and all that, these are some of the things that might be driving that reality. So some applications of the SciPy spatial module include things usage in machine learning, robotics, GIS system, that's geographical information system, then computer graphics, data science, and scientific computing, which is actually the title of this playlist. So let's go straight and talk about some distance computations. The SciPy.Spatial.Distance module provides many distance metrics. Common metrics include the Euclidean distance, which is one of the most popular distance we talk about in mathematics. Then you have Manhattan distance, Minkowski distance, cosine distance, Hamming distance, and of course correlation distance. So distance computations are fundamental in areas like clustering. Of course, clustering is you have clustering algorithms under, I believe, um it's unsupervised learning in machine learning, right? Then you have it in recommendation systems, similarity analysis. Similarity analysis, you have it in different fields, especially in natural language processing. Then you have spatial search and machine learning also. So all of these things keep overlapping here and there. So going straight to the Euclidean distance, this is one of the most used distances, right? If you look at when I taught coordinate geometry, this came up a lot there. Even in complex analysis, at some point we get to, I mean, the whole essence of the absolute value of a complex number ends up yielding something, okay, maybe not quite like this, right? But, we have this kind of thing for coordinate geometry. So Euclidean distance measures straight line distance between 2 points. So, and generally speaking, you have xy. So you have summation of xi minus yi all squared like that. So maybe x1 minus y1 squared plus x2 minus y2 squared and so on and so forth. So if you have and you can see this in terms of data sets, like all this xi now could just be x of talking about a particular idea, and y is another set of, this is a variable, yi is another variable like that. So you want to measure the similarities and things like that. So some things you need to import include NumPy as NP for numerical Python, Matplotlib for data visualization, then SciPy spatial distance. SciPy spatial, from SciPy spatial, you can have the distance function, KDTree, cKDTree, convex hull, Delaunay, Voronoi, and Voronoi plot 2D like that. So I'll run that so that other things can work properly following that. And then we come to the idea of Euclidean distance, which has already been defined as the summation of the differences between pairs of points. The square of that even. So Euclidean distance here, imagine from SciPy to spatial import distance, which you need. So imagine point one is 1, 2, and point two is 4, 6. Then the Euclidean distance will have to be things like, so if that these are your x values and these are your y values now. So you then have distance that Euclidean point one, point two, and that will be something like square root, right? So you have square root of 4 minus 1. Yeah. So you have 4 minus 1 squared, that is 3. That's 3 squared, that's 9. Then 6 minus 2, that's 4 squared. So 3 squared plus 4 squared. All right. Then you now take the square root of that. So 3 squared is 9, 4 squared is 16. 4 plus 9 plus 16 is 25. Square root of 25, that is actually 5. Like this. Then, well, you can make the points as many as possible. So if I add point 3 to it, which is 3 comma 5, and then I just come here and do point 3 and just add point 3. So I have 3 points now. So I still get some result like that. So you can do as many points as you want. So that's the Euclidean distance. Then for Manhattan distance, you can see that Manhattan distance is almost like Euclidean distance, except the basic, you already always have that basic of xi minus yi. But here you have summation of all the xi minus xy minus yi's, then with the square root taken. But on this other hand now, it's just the summation of all the absolute values, summation of all the absolute value of the differences. So Manhattan distance is also called city block distance or taxi cab distance. So the formula is D equals summation of the absolute value of xi minus yi. So in this case now, if you have xi minus yi, so instead of finding the difference and then squaring the difference and summing them up and then taking square roots. You don't do that. All you just need to do is just say 4 minus 1, 3, 6 minus 2, 4, 3 plus 4, 7. That's what Manhattan distance is all about. Then you have the Minkowski distance. Now you see Minkowski distance generalizes several distance matrix. So for so the Minkowski distance, you see that when P is equal to 1, it becomes the Manhattan distance. So when P is 1, you have 1 over 1 gone. Then this now is 1. And then you have all this summation. So it's Manhattan distance. But when P is equal to 2, it becomes Euclidean distance. The first one we saw. This will now be 1 over 2. That's square root of this summation of xi minus yi raised power 2. So it's as good as the Euclidean distance. So Minkowski distance is a generalization of the Manhattan and Euclidean, several distance metrics, by the way. And then the value of P then determines what you see. So the Minkowski distance example. So if you have point 1 to be 1 to, it's the same 1, 2, 4, 6 we've been using all along. So yeah, if you have point 1 to and point 2, which is 4, 6, then results is distance dot Minkowski, point 1, point 2, P is 3. So for instance, if P is 1, we get what we got for P equals on that 7. That'll be 7 here, as you can see. If P is equal to 2, we get 5, like we got for Euclidean distance. But now if P is 3, it becomes the proper Minkowski. So you have 4.49. What if P is, let me go take P to be 10, we have, so you see it's hovering around 4, 4 like that. Then we have cosine distance. So the cosine distance is the cosine distance measures angular separation between vectors. Okay, and it is widely used in natural language processing, recommendation systems, and search engines. The formula is 1 minus the dot product of x and y. So in this sense, just assume that x is for a particular a data, maybe a column, a variable in a data set, and y is another variable in a data set with several data points. So just imagine that, and then you have the modulus of x and multiplied by the modulus of y, like that. So 1 minus all that gives you the cosine distance. So if you have vector 1 to be 1, 1, 0, and vector 2 is 1, 0, 1, so the result is distance dot cosine vector 1, vector 2, and you have the cosine distance to be 0.5. So that talks about the idea of cosine similarities. Then we have Hamming distance. Hamming distance measures the fraction of differing positions between vectors. So if x is 1, 0, 1, 1 and y is 1, 1, 0, 1, so the result will be distance that Hamming x comma y, then Hamming distance then is equal to 0.5, like this. Then we have pairwise distance matrix. Pairwise distance matrix. Pairwise distance computation calculates distance between every pair of points. So SciPy provides pdist, that's condensed pairwise distances, and square form, which converts condensed vector into square matrix. So imagine this now, that from SciPy.Spatial distance, you import pdist and then square form. So if you have this point 0, 0, 1, 0, 0, 1, so the pairwise distance for the points now, the metric, if it is Euclidean, you get 1, 1, 1.14. Like if I run this, did I run the previous one? I think I did. Okay, I didn't run this one, but it's okay. I don't think it's such a big issue because they are not the previous subsequent ones are not necessarily dependent on them. So you can change it to Minkowski if you like. So it's Euclidean here. You can make it what's the other one now? We have Euclidean, we have what's the second one we did? Manhattan. You have Manhattan. So you can, if you don't want to use Euclidean, you can change it to Manhattan. Control Z. Manhattan. So this one is 111.1 point. That's root 2 in short. Okay, Manhattan is not working here. So, okay, let me just leave it the way it is. Euclidean, right? So, have that. Okay, so if for pairwise distance matrix conversion now, so you now have you have your pairwise here for PDist, and then using Euclidean, you get this. Then for pairwise distance matrix conversion, so you have the square form. So you have 0, 1, 1, 1, 0, square root of 2. This is 1.41 for the square root of 2. Then you have 1 root 2, 0, like this. So, I mean, the math behind this, you can imagine how tedious it can be, but thankfully, computing helps to simplify some of this mathematically expensive ideas, computationally expensive ideas. So cross-distance computation, CDist computes distances between two collections of points. So you have, from SciPy to spatial the distance import cdist, and then A is 0011, B is 2233. So, and the results using, so you want to find the distance between these two. Now that's cross distance computation. You have two matrices and you want to compute the cross distance between them. So you have the result is now C dist, that's cross distance between A and B, and the metric is Euclidean, and you have 2.82. It's looking like 2 root 2. 2.82 should be 2 root 2. Yeah, and you have 4.24. So you see that this one's is like the first row is like twice of the second row. So that's going to be like some kind of uh some is it redundant matrix. When we're dealing with linear algebra, we know how to call this kind of thing. That they are linearly dependent, exactly. They are linearly dependent because say row 2 is twice row 1 is twice row 2. Yeah. Oh, not exactly, not exactly, not exactly. There are some relationships, but not like the way I've said it. Yeah. Okay, so this is 2 root 2. This is root 2. This is 2 root 2 again. And then this 4.24 is a bit different from all of that. All right, so we have KDTree. A KDTree is a binary space partitioning tree, and the purpose is for fast nearest neighbor search, efficient spatial queries, and reduced search complexity. So applications are in robotics, GIS systems, recommendation engines, and image processing, and of course clustering. So if you have yeah, if you're building a KD tree now and you have points 2, 3, 5, 4, 9, 6, 4, 7, 8, 1, 7, 2. I mean, you can see this as you can use longitude and latitude for this, right? And see, how these things compare. So then you can build your KD tree by just saying KD tree equals KD tree of the points, and then you print the KD tree. So if you print that, it gives you something that has been built. But then where you can now begin to use it is you can begin to query your KD tree. So the query method finds nearest neighbors efficiently. So query point, if you have a query point 6,3, be sure the 6,3 is not here. So let's say these ones have been fixed already, and then you are at a location 6,3 and you want to find the distance value and the index. So it's just a KDTree query of the query point. So you want to print the distance. So distance value and then the nearest point to it. So the distance is 1.414. So it's more like you are stranded somewhere. Maybe you need to buy gas for your car. You are stranded somewhere and you have just enough gas to get to the next filling station, no matter fuel station, no matter where that is. Okay, so you can quickly find, okay, from here, just like what you do on Google Map, like nearest filling station, nearest gas station. So you're at 6.3 and you want to find the nearest point to you where there's a gas station. So it tells you, okay, the nearest point is 5,4, maybe in terms of long and lat, and then the distance is 1.414, like that. Okay. So that's the kind of thing happening there. So you can also do multiple neighbor search. So imagine that you have distances, indices, KD tree query points, K is 3. So and then you print the distances and the indices. So you want to print nearest neighbors for index and indices now. So you print points corresponding with the indices. So for the distances now, you have 1.414, 1.414, 2.82, and the indices are 154. So the nearest neighbors are 54. So to 0.63, now that 0.63 we used the other time, which is the query point, and that's the same thing we are using here. So the nearest 3 points to 63, of course, we already knew it was 54. There was 54 there. So the next one, so it's more like you want to see more options. So here you have 1.414. The distance is 1.414, and the nearest point corresponding to that is 5, 4, which you already saw before. Then 7, 2 is also 1.414, same distance. So you can now choose, okay, if this one for 1.414 will mean you are going back, and then there's another for 1.414, which means you are going ahead. So you can choose to go to 1.414 ahead, so that it's not like, so that way you have covered that distance and you don't have to do it twice. So you can, so now you have options. So the other time we got only 5, 4, which felt like the only option, but now you see 0.72 is another option, which is just one same distance like 5, 4 from the 0.6, 3, which we are currently located. Then 8, 1 is twice of each of the distances. So you know you want to check your options to and decide. Then we have cKDTree. cKDTree is a faster C optimized implementation of KDTree, and the advantages include faster execution, lower memory usage, and better scalability of large data sets. So cKDTree now. So if you have tree, is cKDTree of the points. So it's the same points we have here, right? So you see points. So it's same point 2, 3, 5, 4, 9, 6, 4, 7, 8, 1, 7, 2. So same for that. And then you want to now you now have the result tree.query 6, 3. So from 6, 3 now, you want to find the nearest distance still. So you have that as 1.414, and it tells you that's the first point right there, which is from this. Okay, yeah, okay, that's actually 5, 4 right there. So we have radius search. You can query underscore ball underscore point finds all points within a specified radius. So it's like, okay, I want something, maybe you're looking for accommodation within a radius of 5 kilometers, or within a radius of 2 kilometers from a university campus where you work or where you school. You know, this is the query ballpoint uh function can work with that for radius search. So you have indices now, tree dot query underscore ball underscore point 6, 3. So it's like the long and lat of your office is 6, 3, assuming. Then r is 3. So you can then print all indices and check. So you have 154. So all these points now, 5, 4, 8, 1, and 7, 2, are all within that radius. I hope you know these indices 1, 4, 5 are referring to the originally declared points. And in Python, right, we refer to points based on starting from 0. So this is like 0, 1, 2, 3, 4, 5. So that's why 1 is 5, 4, like that. So 5 is 7, 2, I believe. 5 is 7, 2, 0, 1, 2, 3, 4, 5, yeah. And then 3, 4 now. 4 is 8, 1, you know, and that's exactly what we have here. So it means that you're looking for a place, you're looking for an accommodation that is maybe k equals 3 from wherever you are. Okay, and these are the options. Then you can see, okay, 5, 4 and 7 to have the same distance. Oh, okay, this is another one. Okay, I'm already talking about radio search here. So you have these three options. So you can then choose based on the distance which one works best for you. Then we have the convex hull. A convex hull is the smallest convex polygon containing all points. So it could be, you know, polygons are uh, a polygon is a plane figure that has at least two that has three or more sides and angles. Like, so that's why a triangle is a polygon. Okay, so at the application here you have for the applications are in shape analysis, collision detection, GIS, image processing, and of course pattern recognition. So imagine you have a convex hull example points. You have 0, 0, 1, 0, 1, 1, 0, 1, 0.5, 0.5, and the hull. Now you get convex hull of all these points now. So if you print hull vertices, you have 0, 1, 2, 3. So apart from that now, you then go ahead and check the convex hull visualization of those points now. So by the time you plot all that, so I know this can also be useful in uh surveying and geoinformatics. Of course, that's like GIS still. So you now have your convex hull now. So this is the smallest polygon accommodating all the points, and the center is somewhere around here. So it's more like if you want to survey a land, and then you know the center you can easily locate somewhere around here. Then you have the Delaunay triangulation. Delaunay triangulation divides points into triangles. So you have properties. It avoids skinny triangles. The property avoids skinny triangles and maximizes minimum triangle angles. Then applications are in mesh generation, terrain modeling, and finite element methods. So the Delaunay triangulation example, if you have try is Delaunay of the point, the same point, the last point declared, right? I think it should be this one. Yeah, this 0, 0, 1, 0, 1, 1, 0, 1, 0.5, 0.5. That's the last point we talked about. So then you print try dot simplices. That's 241140342. So yeah, these are triangles formed around what you have there. So the learning visualization, now you have plots, triplots, points, 0, 1, and all that. And then you have something like this. Oh, I didn't run this. That's why it's giving that error. So I run this so that this can work. Yeah, that's it. So each point becomes like a triangle that is not overlapping. So then you have Voronoi diagrams. Voronoi diagrams partition space into regions. So each region contains points closest to one generating point. Applications involve things like cellular networks, GIS systems, meteorology, biology, resource allocation. So, in politics, right? You get to administer properly. You have to divide. You have to divide up spaces into maybe regions, quarters, prefectures, cities, and all of these kind of things for better resource allocation and management. So Voronoi diagram example now. So VOR is Voronoi of the same points we used before. Then you print the Voronoi vertices, which are 1, 0.5, 0.50, 0.51, and 0.5, like that. And then the Voronoi this visualization now becomes like what we have here now. So you have so we said it's partition space into regions. So you have that space now, and then you have, you have various regions like that. So you have this, and even the one in between. Then we're talking about algorithm complexity now. So brute force nearest neighbor is of order n, whereas KDTree nearest neighbor is log n. Of course, you can be sure log n is faster than order. I mean, once this is 10, log 10 is 1. So this looks faster than n. Then n squared, of course, okay, yeah, it looks like n squared will be faster than log n, depending on some ideas. Then convex hull is order n log n. Delaunay triangulation is also order n log n. So you want to see, depending on what you're working on, you want to see which one works best for your data. So you have real world examples. For instance, you're looking for the nearest restaurant to your location. So imagine, so you have the restaurants all listed, probably on Google Map or somewhere, and you have their longitude and latitude. Let's say the longitude and latitude, this is hypothetical, by the way. So you have 2, 3, 5, 4, 9, 6, 4, 7, 8, 1, and 7, 2. And your customer location, your location as the customer is 6, 3. Maybe you're at home and you want to go to the nearest restaurant, right? So then you do your restaurant underscore tree, which is cKDTree of the restaurant, and then you query restaurant underscore tree dot query of the customer location. So you're looking for my location, which are the nearest restaurant. Then the nearest restaurant will now be restaurants in the ID in the index. So then you print the nearest restaurant. So if you do that, you get the nearest restaurant with 5,4. So, but of course, you could also want to detect more than one so that I know their distances. So in that case, you can use the example I had used the other time. You can also do some collision detection. So you have objects at 1, 1, 2, 2, 8, 8, 9, 9. The collision tree will now be cKDTree of the objects. Then, of course, that's a NumPy array in this case. So the pairs are collision tree dot query pairs are equals to. So you do that, and then you can detect pairs that can help you avoid collision like that. Then benchmarking KDTree. So if you so here we need time. So large points, you have random value 100,000, comma 2, and then your query is np random dot rand 2 start time dot time. For points and large points, linear algebra, take the norm of point minus the query, and then brute force time, you have time minus start, then start is time dot time. So here we are dealing with some time thing like that, and then you do the cKDTree of the large points and do the query, and by the time you run all of that, okay, that's I've left the page. Okay, we're back there. So we are benchmarking KDTree, right? So here now you have brute force time, that's 1.00 something, whereas the KDTree time is like 10% of the brute force time, like that. So you see the KDTree actually works faster. It's faster to use KDTree for benchmarking to do your stuff, right? Then practical visualization of the convex hull point that we did the other time. So imagine random seed helps you to preserve the values so that it doesn't keep changing, because since you're dealing with random stuff, then the hull, now you have the convex hull of all the points. So you're generating some point 30 by 2, you know, and you have the convex hull points. So that gives you the smallest polygon that accommodates all the points you have. And this is something like the random points with convex hull here. Then complete combined example now. So you have cKDTree convex hull and everything put together. So you want to check out the code. Don't forget the code sheets are available. You can access them through the link leading to the Google Drive, either on Facebook or on YouTube, right? So here now we put everything together. So you have your query. This is like your location. Then the nearest point to it is this green one, and then these are other points like that. Okay. So best practices, you want to use cKDTree for performance. That's to make it faster. Tree is cKDTree of whatever data you have. Then avoid huge pairwise distance matrices. Then avoid square form pdist big underscore data for very large data sets, because memory usage grows quadratically. So if you want to use square form, it's better you use it with small data set. Then normalize data from sklearn does preprocessing import standard scalar. So you can have you can you can normalize your data if the values are too big for easier handling. And then you should be careful with high dimensions. KDTree performance degrades in high dimensional spaces due to the curse of dimensionality. Then in conclusion, we see that the SciPy.Spatial Module is an essential toolkit for spatial computation, geometric analysis, scientific computing, machine learning, GIS systems, and of course, robotics. So far we learned about distance metrics, pairwise computations, KDTree and cKDTree, convex hulls, Delaunay triangulations, Voronoi diagrams, performance optimization, real-world spatial applications. So if you're a geographer, a geomatic engineer, a GIS person, an architect, all you have to do with space. This SciPy.Spatial can be very useful for you. So mastering this module provides a strong foundation for advanced computational geometry and spatial analysis. So if you deal with space in general, this is a SciPy module you want to really consider. That's SciPy.Spatial. So problem one, Euclidean distance. Create 2D points and compute the Euclidean distance between them using distance.Euclidean. That's the kind of thing we've done before. For Manhattan distance, compute the Manhattan distance between 1, 2, and 7, 9. Of course, that'll be 7 minus 1. That's 6. 9 minus 2, that's 7. So 6 plus 7 is 13. That's the Manhattan distance. Then Minkowski distance, compute the Minkowski distance with p equals 3 between two vectors. So you pick any two vectors and do that. Then 4 upwards. So let's say 4 to 7 now. So you have cosine distance, create two vectors and compute cosine distance, cosine similarity. Then Hamming distance, compute the Hamming distance between two binary vectors. Just pick the vectors and compute. Pairwise distance matrix, generate 5 random 2D points and compute. Pairwise distance using pdist. And of course, square distance matrix using square form. Then 7 cross distance matrix. Create two dataset A with 3 points, dataset B with 4 points, and compute all distances between the datasets using cross distance matrix. Then you have KDTree construction. So generate 100 random points and build a KDTree. Print the 3 objects. Then problem 9, nearest neighbor search. Using a KDTree, query the nearest neighbor to a random point. Print nearest point, distance, and in the index. Then k nearest neighbors. Find the k equals 5 nearest neighbors for a query point. Then you have radius search. So you want to find something within a given radius. So use query underscore ball underscore point. Find all points within radius r equals 0.2. Then cKDTree performance. Compare KDTree and cKDTree for nearest neighbor search on 100,000 random points and measure execution time. Problem 13, convex hull. Generate 30 random 2D points and compute the convex hull, print hull vertices. Then problem 14, so convex hull visualization. Visualize random points, convex hull edges using Matplotlib. Then you have the Delaunay triangulation. Generate random points and compute the Delaunay triangulation. Print triangle simplices. Then Delaunay visualization. Visualize the Delaunay triangulation using plot.try-plots. Then problem 17, Voronoi diagram. Generate 15 random points and generate a Voronoi diagram. Print Voronoi vertices. And of course, you have the last set. Voronoi visualization. Visualize the Voronoi diagram using Voronoi plot 2D, then collision detection, then mini spatial search engine. You want to work with all of this. So build a mini location search system, generate 1,000 random locations, build cKDTree, query nearest location, 5 nearest locations. So some of these things we've done before, you just need to adapt to what you need to just adapt some of those codes to these new realities. Thank you so much for listening. Let me know how helpful this is for you. Um, if you have subscribed to this channel already, I thank you for that. If you have not subscribed, why not go ahead and subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. This gives you special privileges like seeing some videos first before others, or seeing some videos exclusively because you're a member of the channel. You can request for PDF copies of my notes, maybe for maths or data science, anything. As far as they're available, you can have them. Then we can also hang out to discuss whatever interests you on my channel, either virtually or physically if you're in the same geographical location at any point in time. All right. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Don't forget, you can get the code sheet from the Google Drive. So you can find the link as a comment on YouTube or on Facebook, and also in the description box. So till I come your way again, keep doing maths, data science, computing, whatever. Keep doing all of them right. Bye.